All right, I want to take a look at our basic identities again now that we have these new definitions and we're looking at trig functions of different angles. I just want to show that the identities are still true. Certainly from the definitions we have the reciprocal identities, that the sine, the sine of theta is defined as y over r, and the cosecant of theta is defined as r over y. So certainly with those definitions, the reciprocal identities are certainly still right. If you take a look at this identity, the tangent of theta is the sine of theta over the cosine of theta, right? Is that true? Well, the sine of theta was y over r. The cosine of theta is x over r. So if I divide those two fractions, you've got y over r times r over x. The r's cancel out, and this is y over x. It doesn't matter whether this is a first quadrant angle or a third quadrant angle or anything, that the x and the y and the r are all going to act together like they did before with the opposite and the adjacent and the hypotenuse. So that quotient identity is still right. If you take a look at the Pythagorean identities, sine squared theta plus cosine squared theta, right? Is that still, I'll put a question mark over the equal sign, is it still equal to 1? Well, the sine of theta is y over r, so squared looks like that. The cosine of theta is x over r, so squared looks like that. Now, x and y might be positive or negative, but when you square them, it doesn't matter. They become positive. So this still looks like y squared over r squared plus x squared over r squared, and you've got a common denominator, so this is y squared plus x squared over r squared. But remember the picture that we're looking at doesn't matter what quadrant you're in. You're looking at that angle. There's an x coordinate and a y coordinate, and r is that hypotenuse, and it's always the case that x squared plus y squared is r squared. So this numerator here is r squared. So I've got r squared over r squared, which is certainly 1. The identity is still true. Similarly, you can show the other two. One of the things I want to look at, we can show the other two Pythagorean identities. So one of the things I want to look at now is the cofunction identities, because these look a little different. For instance, the cofunction identity, one of them was that the cosine of an angle is the sine of the complementary angle, right? These were the cofunction identities. Well, what if you have like a bigger angle? What if you've got an angle that's out here in the second quadrant, right? The complement then is this negative angle coming back to there, right? So let's take a look here. If I've got an x coordinate and a y coordinate here, the x is negative, the y is positive. The complementary angle is this negative angle, which is actually down here. Right? Actually, I made it look like those line up, and I don't think they do, so let me redraw that picture. It's down here. Right? Well, this angle here is the same as that little angle right there, which it turns out is the same as this angle up here. I've got parallel lines, transversal, alternate interior. So whatever this length there is the same as this. So the y coordinate, let's call this, just for the sake of argument, let's call this capital Y. It's going to equal that little x right there. Although where this is negative, that's also negative, right? And this side right here, which I'm going to call capital X, because this triangle is the same as that one, it's this little y. So when I look at the cosine of this angle theta, I'm looking at x over r, when I look at the sine of 90 minus theta, so when I look at this complementary angle down here, the sine is its opposite over r, but that opposite, this y value, was the x value that you had over there. And so indeed, they're still the same. Let's do that with a particular example here, where I can actually put some numbers in. So for instance, if I use 120 degrees, so here's my angle, put a 120 degree angle in there. Right? The complement of 120 degrees, if I look at 90 minus 120, that's negative 30. So the complementary angle is down here. Whoops, that was pretty ugly looking 30 degree angle. So it's down here like that. If I drop a perpendicular in either place, here I've got a 60 degree angle. So I've got a 1 to 2 to the square root of 3 triangle, right? That's the 30 degree angle, 60 degree angle, 90 degree angle. This is a negative here. Here I've got a 30 degree angle, and a right angle, so this must be 60 down here. So again, I've got a 1 to 2 to the square root of 3. But here the y coordinate is negative, so let me give myself a little bit more room to put the negative sign in there. Right? When I look at the cosine of 120 degrees, that's going to be x over r, so negative 1 over 2. When I look at the sine of the complementary angle is negative 30. That's going to be the y coordinate here over r. Remember, I have to put it in standard position. So the y coordinate over r is negative 1 over 2. They're equal to each other. Right? Doesn't matter that we're using bigger angles now, or maybe even negative angles. The trig identities that we saw before, those basic identities, are still true.